Hello! Today, we're going to dive into the fascinating world of trigonometry. By the end of this comprehensive lesson, you'll have a solid foundation in the core concepts of this essential branch of mathematics. We'll start with the basics, covering the fundamental trigonometric ratios. Then, we'll explore the powerful Pythagorean identity. After that, we'll learn how to solve trigonometric equations. We'll also look at other important identities, the angle sum and difference formulas, and finally, the law of sines and law of cosines. Let's get started. Our first goal is to understand the basic trigonometric ratios. By the end of this section, you will be able to define and calculate sine, cosine, and tangent for angles in a right-angled triangle. Let's begin with a right-angled triangle. Remember, a right-angled triangle is a triangle with one angle that measures exactly 90 degrees. Now let's pick one of the other two angles and call it theta. From the perspective of this angle theta, we can label the three sides of the triangle. The side directly opposite the angle theta is called the opposite side. The side next to the angle theta, which is not the hypotenuse, is called the adjacent side. And the longest side, which is always opposite the right angle, is called the hypotenuse. These three sides form the basis for our three main trigonometric ratios: sine, cosine, and tangent. Sine of theta is the ratio of the length of the opposite side to the length of the hypotenuse. Cosine of theta is the ratio of the adjacent side to the hypotenuse. And tangent of theta is the ratio of the opposite side to the adjacent side. A common mnemonic to help you remember these is SOHCAHTOA. SOH stands for sine, is opposite over hypotenuse. CAH stands for cosine, is adjacent over hypotenuse. And TOA stands for tangent, is opposite over adjacent. This is a very helpful tool for recalling these definitions. Let's work through an example. Suppose we have a right-angled triangle with an angle theta. Let's say the side opposite theta is 3 units long, and the hypotenuse is 5 units long. We want to find the sine of theta. Using our definition, sine of theta is opposite over hypotenuse. So we have 3 divided by 5. The sine of this angle theta is 3/5. Now what if we wanted to find the cosine and tangent? We'd need the length of the adjacent side. We can find this using the Pythagorean theorem. The Pythagorean theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So a squared plus b squared equals c squared. In our triangle, the opposite side is a, the adjacent side is b, and the hypotenuse is c dur. Plugging in our values, we get 3 squared plus b squared equals 5 squared. That's 9 plus b squared equals 25. Subtracting 9 from both sides gives us b squared equals 16. Taking the square root, we find that b, our adjacent side, is 4. Now that we have all 3 sides, we can find the cosine and tangent. Cosine of theta is adjacent over hypotenuse, which is 4 over 5. Tangent of theta is opposite over adjacent, which is 3 over 4. So we've successfully found all 3 basic ratios for this triangle. Now let's look at some common angles: 30, 45, and 60 degrees. It's very useful to know the exact trigonometric values for these angles. We can derive these values from 2 special triangles, the 4-5-4-5-9-0 triangle and the 3-0-6-0-9-0 triangle. For the 4-5-4-5-9-0 triangle, the 2 legs are equal. If we set them to 1, the hypotenuse is the square root of 2. From this, we can see that sine of 45 degrees is 1 over root 2, cosine of 45 degrees is also 1 over root 2, and tangent of 45 degrees is 1. For the 3-0-6-0-9-0 triangle, the sides are in the ratio 1 to root 3 to 2. Using this, we find that sine of 30 degrees is 1/2, cosine of 30 degrees is root 3 over 2, and tangent of 30 degrees is 1 over root 3. For 60 degrees, sine is root 3 over 2, cosine is 1/2, and tangent is root 3. Let's quickly recap. We've defined the basic trigonometric ratios, sine, cosine, and tangent, using the sides of a right-angled triangle. We also saw how to use the Pythagorean theorem to find a missing side, and calculated the exact values for common angles, like 30, 45, and 60 degrees. You are now able to define and calculate these ratios. Next up is a very important relationship in trigonometry. Our goal here is to understand and apply the Pythagorean identity to find missing trigonometric values. This identity is a direct consequence of the Pythagorean theorem we just discussed. Let's start with a right-angled triangle in the unit circle. The unit circle is a circle with a radius of 1, centered at the origin. If we draw a right triangle inside this circle, with the angle theta at the center, the hypotenuse is the radius, which is 1. The adjacent side is the x-coordinate of the point on the circle, and the opposite side is the y-coordinate. Now, let's apply our SOH, CAH, TOA definitions. Sine of theta is opposite over hypotenuse, which is y over 1, or just y. Cosine of theta is adjacent over hypotenuse, which is x over 1, or just x. So, on the unit circle, the x-coordinate is cosine of theta, and the y-coordinate is sine of theta. Now, let's apply the Pythagorean theorem to this triangle. The theorem states that the square of the adjacent side plus the square of the opposite side equals the square of the hypotenuse. So x squared plus y squared equals 1 squared. Since x is cosine of theta and y is sine of theta, we can substitute those into the equation. This gives us cosine squared of theta plus sine squared of theta equals 1. This is the Pythagorean identity. It's a fundamental relationship that holds true for any angle theta. Let's see how we can use this. Suppose we know the value of one trigonometric ratio and want to find another. For example, let's say we know that sine of theta is 3/5 and we want to find cosine of theta. We start with the identity. Sine squared plus cosine squared equals 1. We substitute 3/5 for sine of theta. Squaring 3/5 gives us 9/25, so 9/25 plus cosine squared equals 1. To solve for cosine squared, we subtract 9/25 from both sides. 1 is the same as 25/25, so 25/25 minus 9/25 is 16/25. This means cosine squared of theta is 16/25. Finally, we take the square root of both sides. The square root of 16/25 is 4/5. Notice that we get both a positive and a negative answer. The sign depends on which quadrant the angle theta is in. For now, we'll assume it's in the first quadrant where all ratios are positive. So we've seen how the Pythagorean identity, cos squared of theta plus sine squared of theta equals 1, is derived from the unit circle and the Pythagorean theorem. We also practice using it to find a missing trigonometric value. You are now able to apply this identity to solve problems. Now that we understand the basic ratios and the Pythagorean identity, let's move on to solving trigonometric equations. Our objective is to solve equations of the form sine of x equals k, cos of x equals k, and tan of x equals k within the interval from 0 to 2 pi. The interval 0 to 2 pi represents one full rotation around the unit circle. We're looking for all the angles in this range that satisfy the equation. Let's start with an example. Suppose we want to solve sine of x equals 1/2. We're looking for the angles x between 0 and 2 pi whose sine is 1/2. The first step is to find the reference angle. This is the acute angle in the first quadrant that satisfies the equation. We ask ourselves, what angle has a sine of 1/2? From our special triangles, we know this is 30 degrees, or pi/6 radians. This is our reference angle. The second step is to determine the quadrants where sine is positive. Remember the mnemonic, all students take calculus. This tells us that all ratios are positive in quadrant I, sine is positive in quadrant 2, tangent is positive in quadrant 3, and cosine is positive in quadrant IV. Since sine is positive in our equation, our solutions must be in quadrant I and quadrant 2. Now we can find our solutions. In quadrant I, the angle is simply the reference angle, so our first solution is x equals pi/6. In quadrant 2, the angle is pi minus the reference angle. So our second solution is x equals pi minus pi/6, which is 5 pi/6. So the solutions to sine x equals 1/2 in the interval 0 to 2 pi are pi/6 and 5 pi/6. Let's try another one. Solve cosine of x equals -√3/2. First, the reference angle. We ignore the negative sign for a moment and ask, what angle has a cosine of √3/2? That's 30 degrees, or pi/6. So our reference angle is pi/6. Second, the quadrants. cosine is negative in quadrant 2 and quadrant 3. So our solutions will be in quadrant 2 and quadrant 3. Third, the solutions. In quadrant 2, the angle is pi minus the reference angle, which is pi minus pi slash 6, or 5 pi slash 6. In quadrant 3, the angle is pi plus the reference angle, which is pi plus pi slash 6, or 7 pi slash 6. The solutions are 5 pi slash 6 and 7 pi slash 6. Let's do one more. Solve tangent of x equals 1. Reference angle. What angle has a tangent of 1? That's 45 degrees, or pi 4. Quadrants. Tangent is positive in quadrant I and quadrant 3. In quadrant I, the solution is pi slash 4. In quadrant 3, the solution is pi plus pi slash 4, which is 5 pi slash 4. The solutions are pi slash 4 and 5 pi slash 4. To recap, we've learned a systematic way to solve basic trigonometric equations. We find the reference angle, determine the correct quadrants using ASTC, and then calculate the solutions. You are now able to solve equations like sine of x equals k, cos of x equals k, and tan of x equals k. In this section, our goal is to understand and verify trigonometric identities. An identity is an equation that is true for all values of the variable for which both sides are defined. Think of it like a mathematical synonym. It's a different way of writing the same thing. We've already seen one, the Pythagorean identity. Let's quickly review it. The Pythagorean identity is sine squared of theta plus cosine squared of theta equals 1. This is a cornerstone of trigonometry. From this one identity, we can derive two more by dividing by sine squared or cosine squared. If we divide every term by cosine squared, we get tangent squared plus 1 equals secant squared. If we divide by sine squared, we get 1 plus cotangent squared equals cosecant squared. These are also Pythagorean identities. Next we have the reciprocal identities. These define the reciprocal functions. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. This means cosecant of theta is 1 over sine of theta, and so on. Finally, we have the quotient identities. Tangent of theta is equal to sine of theta divided by cosine of theta. And cotangent of theta is the reciprocal of that, cosine of theta divided by sine of theta. Now, let's see how to use these to verify a more complex identity. The goal is to show that one side of the equation can be transformed into the other side using our known identities. Let's verify the identity. Tangent of x plus cotangent of x equals secant of x times cosecant of x. A good strategy is to start with the more complicated side and try to simplify it. In this case, the left side looks more complex. We'll start with the left side. Tangent of x plus cotangent of x. The next step is often to rewrite everything in terms of sine and cosine using the quotient identities. Tangent is sine over cosine, and cotangent is cosine over sine. So we have sine of x over cosine of x plus cosine of x over sine of x. Now, we need to add these fractions. To do that, we find a common denominator, which is cosine of x times sine of x. We multiply the first fraction by sine over sine, and the second by cosine over cosine. This gives us sine squared of x plus cosine squared of x, all over cosine of x times sine of x. Look at the numerator. Sine squared plus cosine squared. That's our Pythagorean identity. We know that sine squared plus cosine squared equals 1, so the numerator simplifies to 1. Our expression is now 1 over cosine of x times sine of x. We're almost there. We can split this fraction into 2. This is the same as 1 over cosine of x times 1 over sine of x. Now we use our reciprocal identities. 1 over cosine is secant, and 1 over sine is cosecant. So our left side simplifies to secant of x times cosecant of x. This is exactly the right side of our original identity. We have successfully verified the identity. We started with one side and, through a series of logical steps using known identities, transformed it into the other side. You are now able to use reciprocal, quotient, and Pythagorean identities to verify other trigonometric identities. In this section, we'll learn how to find the sine, cosine, and tangent of the sum or difference of two angles. Our goal is to understand and apply the angle sum and difference formulas. These formulas are incredibly useful because they allow us to find the exact trigonometric values for angles that aren't on our special triangles by breaking them down into angles we do know. Let's start with the sine formulas. The sine of the sum of two angles, A and B, is sine A cosine B plus cosine A sine B. The sign of the difference is very similar, but with a minus sign in the middle. Sine A cosine B minus cosine A sine A. Now for the cosine formulas. The cosine of the sum is cosine A cosine B minus sine A sine B. Notice the sign is opposite here. The cosine of the difference is cosine A cosine B plus sine A sine B. Again, the sign is opposite. And finally, the tangent formulas. The tangent of the sum is tangent A plus tangent B, all over 1 minus tangent A tangent B. The tangent of the difference is tangent A minus tangent B, all over 1 plus tangent A tangent B. The signs in the numerator match the operation, and the signs in the denominator are opposite. Let's put these into practice. Suppose we want to find the exact value of sine of 75 degrees. We don't know sine of 75 degrees off the top of our heads, but we can write 75 as the sum of two angles we do know, 45 degrees and 30 degrees. So we'll use the sine sum formula, with A equals 45 degrees and B equals 30 degrees. The formula is sine A cosine B plus cosine A sine B. Plugging in our angles, we get sine of 45 degrees times cosine of 30 degrees plus cosine of 45 degrees times sine of 30 degrees. Now we substitute the exact values from our special triangles. Sine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. Cosine of 45 is root 2 over 2. And sine of 30 is 1/2. Multiplying the fractions, we get root 6 over 4 plus root 2 over 4. Combining them, the exact value of sine of 75 degrees is root 6 plus root 2 all over 4. Let's try a cosine example. Find the exact value of cosine of 15 degrees. We can write 15 degrees as the difference between 45 and 30 degrees, so we'll use the cosine difference formula. The formula is cosine A cosine B plus sine A sine B. Plugging in our angles, we get cosine of 45 degrees times cosine of 30 degrees plus sine of 45 degrees times sine of 30 degrees. Again, we substitute the exact values. This gives us root 2 over 2 times root 3 over 2 plus root 2 over 2 times 1/2. Multiplying and combining, we get root 6 plus root 2 all over 4. Interestingly, this is the same value as sine of 75 degrees. This is not a coincidence, but a property of complementary angles. To summarize, we've introduced the angle sum and difference formulas for sine, cosine, and tangent. We then use these formulas to find the exact values of trigonometric functions for angles like 75 and 15 degrees. You are now able to calculate the sine, cosine, and tangent of sums and differences of angles. In our final section, we'll move beyond right-angled triangles and learn how to solve for unknown sides and angles in any triangle. Our goal is to understand and apply the law of sines and the law of cosines. These two laws are incredibly powerful tools for solving oblique triangles, which are triangles that do not have a right angle. Let's start with the law of sines. Consider a triangle with angles A, B, and C, and the sides opposite them labeled A, B, and C respectively. The law of sines states that the ratio of a side to the sine of its opposite angle is constant for all three sides of the triangle. That is, A over sine A equals B over sine B equals C over sine C. We use the law of sines when we know a side and its opposite angle, and we want to find another side or angle. This is often called the angle-side angle, ASA, or angle-angle-side, AAS case. Let's look at an example. Suppose we have a triangle where angle A is 40 degrees, angle B is 60 degrees, and side A is 10 units long. We want to find the length of side B. We set up the law of sines. We know A, and we know B, and want to find B. So we use the part of the law that relates these four values. To solve for b, we multiply both sides by sine of 60 degrees. So b equals 10 times sine of 60 degrees divided by sine of 40 degrees. Using a calculator, we find that b is approximately 13.47 units. Now let's introduce the law of cosines. The law of cosines is a generalization of the Pythagorean theorem. It relates the three sides of a triangle to the cosine of one of its angles. Notice that if angle A were 90 degrees, cosine of A would be 0, and the formula would simplify to a squared equals b squared plus c squared, which is the Pythagorean theorem. This shows the connection. We use the law of cosines when we don't have a side and its opposite angle. This happens in two main cases: side angle side, SAS, where we know two sides and the angle between them, or side side side, SSS, where we know all three sides. Let's try an SAS example. Suppose we have a triangle where side B is 8, side C is 12, and the angle A between them is 70 degrees. We want to find the length of side A. We use the first form of the law of cosines. We plug in our values. A squared equals 8 squared plus 12 squared, minus 2 times 8 times 12, times cosine of 70 degrees. Calculating this, we get 64 plus 144 minus 192 times approximately 0.342. This simplifies to 208 minus about 65.66, which is 142.34. Taking the square root, we find that side A is approximately 11.93 units long. To recap, we've learned two powerful laws for solving any triangle. The law of sines is used when you have a side and its opposite angle, and the law of cosines is used when you have two sides and the included angle, or all three sides. You are now able to use these laws to solve for unknown sides and angles in any triangle. And that brings us to the end of our comprehensive trigonometry lesson. Let's quickly recap what we've covered. We started with the basics, defining sine, cosine, and tangent using SOHCAHTOA. We then explored the fundamental Pythagorean identity, sine squared plus cosine squared equals 1. We learned how to solve trigonometric equations by finding reference angles and using the ASTC rule. We verified identities using reciprocal, quotient, and Pythagorean identities. We used angle sum and difference formulas to find exact values for new angles. And finally, we learned to solve any triangle using the law of sines and the law of cosines. Trigonometry is a vast and beautiful subject, and these concepts are the building blocks for more advanced topics in mathematics, physics, and engineering. I encourage you to practice these concepts with the provided questions to solidify your understanding. Thank you for joining me, and happy learning.